In this video, we'll discuss energy of a capacitor, or in a capacitor. Ultimately, it's the energy contained in the electric field. So as we charge a capacitor, we have a voltage across the capacitor, and that's Q, the charge, over the capacitance. So all the charge that's in the capacitor divided by the capacitance is the voltage across it. Those are maximum values, the ending values that we get when we do such a thing. Now, while it's charging, this isn't an instantaneous process. While it's charging, we use little q and little v, such that little v, the intermediate voltage, is intermediate charge over the capacitance. So v and q are functions of time. They're not maximum values immediately. This is a time-dependent process, and it takes work to move those charges onto the capacitor plates. Sure it does. I mean, if you take a positive charge and move onto a positive plate, it's resisting that. They're repelling. So they don't want to go there on their own. So let's consider differential work. dW is V dQ. Work is volts times charge. And for every little dq that we move, the V is changing a little bit. So we do need to do an integral here. Now V is Q over C. So there's, again, as the charge increases, the voltage increases because of this connection between volts and charge. So then it gets harder and harder to move those little dq's onto the capacitor plate. So the work is the integral of all the dw's until all the work is accounted for. And that's 1 over c, integral from 0 to q of q dq. So we integrate q until all the charge is accounted for. And that's 1 over c. If we integrate q dq, we get q squared over 2. Put the big Q in for little q, and we get q squared over 2. So that the work in charging a capacitor is q squared over 2c. That's what it takes to charge it, which is also equivalent to the work done by the conservative force on the charge to push it back off or to discharge the capacitor. So to see this sort of reciprocal relationship, consider the uncharged capacitor, no charge initially. Work is done by an external force to charge it, so it gets the charge. And once it's charged, that's positive work. Work external is positive. Once it's charged, to discharge it, the conservative force does positive work. The electric field does positive work to discharge it so that it's, once again, uncharged. And now let's summarize some of these results. So a little summary of the energy in a capacitor. We have U is equal to Q squared over 2C that we just analyzed. Now Q is equal to CV, or VC, so it's VC quantity squared over 2C. One of the C's goes away there, and we have 1/2 CV squared. Now that's also 1/2 Q times V, because CV squared is CV times V, and CV is Q, so there you go, equivalent expressions. Now this can be thought of in equivalent terms to things we're already familiar with, like 1/2 1 over c q squared is 1/2 kx squared, where q is related to x, or 1/2 cv squared, 1/2 mv squared, where the voltage is related to the speed. Now all these forms being equivalent, if you look at this final one, 1/2 q times v, what this functionally tells us is that the energy contained in the capacitor is, q times v is work, right? So, or energy. So it's 1/2 of the maximum q times the maximum v. Well, the first charges you put on the capacitor plate, the v hasn't built up, so v is very small. So it takes almost no effort to put the little dq's onto the plate at first. But as the q's build up, v builds up, and it gets harder and harder to put those little dq's on there. So it starts being real easy and goes to maximum difficulty at the end. The average of that is just 1/2 the maximum values. That should make sense. So that's kind of like charge multiplied by the average value of the voltage. And that is the energy in the capacitor. That's why it's the 1/2 and not just QV. Now, field energy, which is really what this is about. The energy in an electric field. Consider two charged parallel plates, separation D, electric field E, surface area A. Well, we've just seen that the energy, I'm going to use this expression, 1/2 CV squared, that's the energy contained in that capacitor. Now, the volume of that region, it's a spatial region, surface area times distance, and we can define a new symbol, U, as the energy density. So energy density, which is energy per volume. So energy per volume, we could put a little volume element inside here, and the energy density in here is the same everywhere else because the electric field is constant everywhere. So this energy per volume is all the energy divided by all the volume, 1/2 CV squared over AD squared. And that's 1/2 of C, which is epsilon 0 A over D, the geometric form. V, let's convert that to E times D squared over AD. Oh, that's nice. A's go away. These D's combine and are erased by these two squared. And we get that the energy density is 1/2 epsilon 0 E squared, which is, interestingly, in an equivalent form to the other forms of energy we've seen in mechanics. 1/2 epsilon 0 E squared shows you that the energy in a capacitor really is in the electric field. Well, let's consider the energy in a spherical capacitor. That should be fun. We already derived the capacitance. There it is. So the energy in a capacitor is Q squared over 2C. We're going to use this form. Well, C is given, so 2C is 8 pi epsilon 0 times AB over B minus A, but it's in the denominator, so those flip around. So there's the energy in a spherical capacitor. And based on how we did this, we can consider this energy from the charge that's been separated or moved into the capacitor. So energy from the charge. Now let's do an analysis I'm sure you'll enjoy. Let's look at this spherical conductor in the center, radius A. Then we have the spherical shell outside of that conducting, radius B with negative Q. Now between the shells, the field is KQ over R squared, and the energy density is 0 everywhere except where there is a non-zero E field. And the only place there's a non-zero E field, because we have this Q inside and negative Q outside. Outside there's no electric field. So only between these two conductors is the only place where the electric field exists. So that's where the energy is contained with a given energy density. So the energy density, 1/2 epsilon 0 E squared that we just derived, 1/2 epsilon 0 electric field, Q over 4 pi epsilon 0 R squared, squared. So let's do the algebra. 1/2 epsilon 0 Q squared over 16 pi squared epsilon 0 squared R to the 4th. And this becomes 32 now. Now the energy is going to be the integral of the energy density, the energy per volume, d volume. So energy per volume, d volume is differential energy. Integrate all the differential energies, we get the entire energy. Let's do it. So U is equal to integral of U dV, energy density, dV, differential volume. So there's our computed U, and the dV is nested differential shells, 4 pi r squared, surface area, dr. So there's our dVs. We have some nice cancellation here, so Q squared over 8 pi epsilon 0, 1 over r squared dr, which is negative Q squared over 8 pi epsilon 0, 1 over r, a to b. And that gives us this result. Negative goes away when I reverse these things. It would be 1 over b minus 1 over a times negative 1. So the energy is q squared over 8 pi epsilon 0, b minus a over ab, which is the same that we got before, but this was looking at the energy in the E field, whereas previously we considered the energy associated with the charge Q. Now they should be the same. But obviously the Q produces the electric field, so we would expect them to be the same. And now let's do a little example. You'll see how easy this is. A joule of electric potential energy exists in 1 cubic meter of space. What's the electric field? So we have 1 joule, 1 cubic meter, and an electric field. Well, the energy density is 1/2 epsilon 0 E squared. So let's solve for E. Multiply by 2, divide by epsilon 0, take the square root, square root of 2u over epsilon 0. Let's plug the numbers in. 2 times u is 1. 1 joule per cubic meter. And there's epsilon 0. So there's our answer. 4.75, well, 475,000 volts per meter is the electric field. And now let's do some more examples and some further development of capacitance concepts.